Hello guys, welcome to the course of classical mechanics. I'm Gautam. Uh, I'm doing my PhD from IIT Kanpur. This course is mainly for bachelor and master's level physics students. The prerequisite of the course are prerequisites are high school level, that is 10 plus 2 physics and mathematics. For example, idea of vector and scalar. Number two, Newton's law of motion. Number three, uh, elementary calculus. So these are the prerequisites of the course. The references, the main text will be classical mechanics by Herbert Goldstein. STEN. Uh, for problems and exercises. So for problems, I will follow the main text. And theoretical mechanics by M.R. Spiegel. There is another very good book for problems and exercises, that is Classical Dynamics by Thornton and Marion. So for theory, I will thoroughly follow the book of Herbert Goldstein, and there are a few other books which I like, but yeah, I mean, I will not follow them, but you can read if you have some extra time. So some other references are number one, Classical Mechanics by David Morin. Number two is Classical Mechanics of course lectures by Professor A. K. Professor A. K. A.K. Roy Choudhury. So these two books you can say these are very good books, and I will mainly follow Goldstein for theory, and for problems I will mainly follow this Goldstein, and apart from that, some problems will be from Spigel, and some problems will be from the Thornton Median. Okay, so today I will discuss only about some elementary mechanics of single particles. These are, I think, if you have 10 plus 2 knowledge, these are very well known. So let me just revise them. To specify the state of a single particle, to specify the state of a single particle, we need its position, which I will denote by the r vector, its position, which is a vector, and its momentum. Okay. And in classical mechanics, this position and momentum, they can be they can be simultaneously measured with 100% precision. So in quantum mechanics, you can't, but in classical mechanics, with 100% precision, you can measure the position and momentum of a particle. So the position, let's say, this is a coordinate. In this coordinate system, a particle is at point P. Sorry, P is already denoted by momentum. So at point Q, and this is the r vector, which denotes the position of the particle. Now, momentum is defined by the mass of the particle times the velocity of the particle. Velocity means how fast the particle is moving, that is the rate of change of its position with respect to time. So what do we do if we need to find the rate of change? We just derivative it. So we just need to derivative the position with respect to time. That is dr dt. So our momentum will be then m dr dt. Now, according to the second law of motion, Newton, force acting on a particle, the external force acting on a particle is given by its rate of change of momentum. So that is the derivative of its momentum with respect to time, how fast its momentum is changing. So if there is no force, the momentum will be constant concept. So let me call it equation 1. So this equation is valid in inertial frame. Now external is equal to d dt of p means mass into velocity. Now this will be equal to m dv dt if m is constant. So if you assume that the mass is not changing, mass is a inherent property of the particle that we cannot change by applying force or something, then F is equal to external force is equal to the mass times the rate of change of velocity. This the rate of change of velocity dv dt. This is called the acceleration. Acceleration. So that means is equal to F external is equal to mass time acceleration. F equal to m. This is a very well-known equation in classical mechanics, in Newtonian mechanics. So where A is dv dt, which is basically ddt of dr. This means d2r dt2, double derivative of the position. So from this equation 1, that is F equal to dp dt. So from equation 1, so if we have a single particle, there is only external force, there is no internal force. If we have more than one particle, then we can have the internal force between the particles and one particle exerting force on another. But for single particle, the external force is the force. So I will denote it only by F from now on for single particle. So which is dp dt. If F is equal to 0, that is no force acting on the particle, then this P is constant. So if there is no force acting on the particle, the momentum of the particle will be constant. This is called the conservation of linear momentum. So linear momentum means P. This P we call linear momentum. Okay. So from the force equation, we get the conservation of linear momentum. Now let's define another thing that is called the angular momentum. Angular momentum, which is defined by a L, that is basically the cross product between the position of the particle and the linear momentum. This means linear momentum is mv, and m is a scalar, so it will We can put it in the beginning and basically r cross v in times r cross v. This is the angular momentum. And another quantity is torque, which is defined by tau, and it is defined as r cross f. So let's see what is the rate of change of this angular momentum. That means dl dt means ddt of r cross p, which is ddt of r cross mv, which is m is a scalar and constant. If we assume, then it will be ddt of r cross v, and then it will be ddt of r, so derivative, so multiplication of two functions, so we can do derivative of first function with second function as it is, and then the first one intact times derivative of the second one, which is dv dt. Now this dr dt, what is the dr dt? The rate of change of position with respect to time, which is basically the velocity. So this will be velocity cross of velocity, and this is r cross, what is this dv dt? This is the acceleration, r cross a. The cross product of two same vectors will be 0, because the cross product of, let's say, two vector a cross b, which will be equal to the magnitude of a, magnitude of the cross product is uh, magnitude of a times magnitude of b into sine theta, where theta is the angle between a and b. So if a and b are the same, then theta is 0 and sine theta will be 0. So the magnitude will be 0. As a result, the cross product will be a 0 vector, null vector. Okay. So then this dl dt, the rate of change of angular momentum, this is equal to m r cross a. Now if I take m with a, then this m a is basically the force. So dl dt is r cross the force, which is defined as the torque. Okay, so this is the torque. You can see r cross f. So torque is basically rate of change of angular momentum. Let's say this is our equation 2. Okay, now we can have a conservation principle here also, like we had before, which is the force was rate of change of linear momentum, and we got the conservation of linear momentum from there. Like if the force is constant, the moment linear momentum is not changing. So here also, if torque is 0, torque is 0, then dl dt is equal to 0 implies L is constant. So this is called the conservation principle of angular momentum. Okay, so we got two conservation principles. Next, we define a new quantity called the work done, called the work. So the work done is a scalar quantity. So previously the things we defined like the torque, the angular momentum, force, and the linear momentum, these are all the vector quantities. Now we define this work, which is a scalar quantity. The work done by force F due to displacement, which is infinitesimal. Infinitesimal means that is tends to zero. So infinitesimal displacement ds is dw, which is scalar product of f and the infinitesimal displacement. So this is a dot product. That means get what we will get is a scalar. So let's say displacement. If we there is a displacement from, let's say, point which is, let's say, from point S1 to S2. Then dw in the net work done in this entire process is integration of dw, which is integration of f dot ds from S1 to S2. So for the entire displacement from S1 to S2, the net work done is the integration of f dot ds. So we cannot always write it as, I mean, not always. In general, it is not f dot S2 minus S1, that is the net displacement. There is the delta S. This is not in general. In general, this is not true. Only when this is not true in general. Only when let me rub it. So only when F is equal to constant, we have a constant force field. So that means F is constant throughout the space or throughout the path for which the displacement is taking place. Then the work done will be F dot S2 minus S1. only for this case when F is constant during the motion. During the motion. Okay. So now what we have is W equal to F dot ds. W equal to integration F dot ds from, let's say, point 1 to point 2. So let's say it goes from point 1 to, from throughout this path it goes to point 2. This means we have the from Newton's second law what we got the expression of AF is from 1 to 2 m times acceleration dot ds. Okay, now m is a constant, so we can put it out of the integration. So is outside the integration, a means dv dt. Now what is ds? Let's see, v means ds dt, right? A bit of change of position. That means ds, which is basically v dt. Okay, so as ds is basically v dt. This means m from point 1 to point 2, we got v dot dv, which is basically m from point 1 to point 2 d of 1 by 2 v dot v. So you can check that. I mean, d of 1 by 2 v dot v, which is equal to 1 by 2 v dot dv plus 1 by 2 dv dot v. Now dot product can commute, so dv dot v is same as v dot dv. So this means we have half of that, half of that, half of that. So it will be v dot d. Okay. So this means, so we can also write it like from 1 to 2 and take m inside, and m v square by 2, where v dot v is basically v square, where v is the magnitude of the velocity, the modulus of velocity. This means the work done from path 1 to 2, from path 1 to 2 is basically of mv square upper lower limit 1, point 1 and upper limit point 2. So let's say it is at point 2 the velocity is v1, and at point 1 if the velocity is and at point 2 if the velocity is v2, and at point 1 if the velocity of the particle is v1, then we can have half m v2 square minus half m v1 square. Now half mv square, this is called the kinetic energy. of the particle. This is called the kinetic energy of the particle. So half mv2 square means the kinetic energy at point 2 minus the kinetic energy at point 1. So work done by force while the displacement is from point 1 to 2 is the change of given by the change of kinetic energy, which is basically kinetic energy at point 2 minus kinetic energy at point 1. Okay, quality equation 3. So now if we have a conservative force, so the force field, if the force field the force field is conservative. Conservative means conservative means conservative means we can always find the scalar v, which is a function of position, such that the scalar function such that force will be equal to minus divergence of v. And its divergence is defined as in Cartesian coordinate, it is defined as I hat del x. It's an operator. So j hat del y, j hat del z. This is how it is defined. Okay. So this v is called the scalar function v is called the potential of the particle, the potential energy of the particle at r. So for conservative force field, the work done W is equal to from 1 to 2 is equal to F dot ds, which is basically from point 1 to 2 divergence of V dot s, divergence of V dot ds. This means V from 1 to 2. This means work done from 1 to 2 is basically V of potential at point R2, the upper limit is not R1, is R2 minus V of R1 is equal to V of R1. If you take the minus inside, and then we will get V of R1 minus V of R2. So we will call it equation 4. So from equation 3 and 4, we get P of R1 minus P of R2 is equal to kinetic energy at point 2 minus kinetic energy at point 1. So kinetic energy at point 2 minus kinetic energy at point 1. This means V of R1, that means potential at point 1, plus kinetic energy at point 1 is equal to potential at point R2, and that means at point 2 plus potential energy at point 2 plus the kinetic energy at point 2. So this is called the total mechanical energy at 1, and this is the total mechanical energy at 2. So what we get is the mechanical energy, total mechanical energy at point 1 is equal to the total mechanical energy at point 2. This is called the conservation of total mechanical energy. This is called the conservation of total mechanical energy. So we got three conservation principles. One is the conservation of linear momentum, another is the conservation of angular momentum, and the third one that written here is called the conservation of total mechanical energy. This is valid for only conservative forces. Okay, so this up to this, it's I mean it's kind of a revise for 10 plus 2 level, and from the next day I will start many particle system, and which will be a little complicated. Okay, so thank you.